Hello guys, in this video we will learn about the quicksort algorithm. Here is the small procedure for the quicksort algorithm. In this procedure, we have passed one array and two indices I and j. I is equal to j when the problem size is small, and if it is not the case, then we consider the problem size as a big problem, and we will partition the array into two parts. Okay, it is not necessarily that both of the parts are in equal size like in merge sort. Here the partition procedure will partition the array based on the pivot element, and we will try to maintain the position of the pivot element as its current position in the array, and it does not require any extra auxiliary sequence in order to sort these elements. So that's why it may be considered as a in-place sorting algorithm. So k will return the index value on which we will partition the arrays, and then we will call the same procedure quicksort on both of the partitioned subarrays. So kth position is elements is already sorted, and for n element, if we pass that n element into the partition procedure, then it will return n minus 1 elements, and one element is already sorted in the array. Okay, so let's understand how the quicksort will partition the array, because the time complexity of partition procedure will affect the recurrence relation of this quicksort algorithm when we divide and combine the both of the partitions. Okay, so let's start with the example. So this is, suppose we want to sort this array, and in quicksort we require a pivot element by which we will partition our subarray. You can consider any pivot element. In some of the books they are considering last element as a pivot element. You can also consider any middle element or any of the element. In this example, let's take the first element as a pivot element. So I will say that the pivot element name is v, and the value of pivot element is 85. Okay, now we have to scan whole array from second element. If I consider pivot element as my first element, then I have to scan all the array from second to last element, and we have to maintain two pointers, one for the second element, suppose this pointer is p, and another pointer at the last element, and suppose it is q, and we will traverse whole array. The p pointer will move forward and q pointer will move backwards, and each pointer will move when it is compared with the pivot element, and the movement is like, if in the direction of p, when I compare the element with p, then I have to look for the greater element than 85. So if you go into this direction, you always find the larger element. When you got the larger element, you will stop. If you go into this direction, then you will always look for the smaller element, and if you found the smaller element, then pivot, then you will stop. So let's scan this array. In the first phase, let's scan this array. You will got the larger element here. When you got the larger element, you will not move this pointer further. So I will stop here and go to the q. This will move if I found the smaller element than the pivot element. So I found the smaller element here itself. So this is also stop. And when both these pointers are stop, then I will check for the condition whether p is less than q. If p is less than q, then I swap these two elements, p and q. So let's write the subsequent resulting array. 85 is a pivot, and I need to swap this one. So 65 is here, then 50, then 77, 45, 37, 90, 10, 120, and 110. So these two elements are replaced. Now pointers are on the same locations where they was earlier. they were earlier. So again pivot is same. I will compare whether this value pointing by P is greater than 85. No. So I will move the pointer P. Until I found the greater element than 85, I will move the pointer P. This is also small. I will again move the pointer. This one, P will pointing to this one. This is also small than pivot. Again 45 is also small than pivot. 37 is also small. 90 is greater. So I will stop here. When I found greater, I will stop. In this one, Q will forward if the element pointed by Q is less than the pivot element. Here 1110 is greater than the pivot element, so I will decrement. It is pointing here. Again this element is also greater, so I will decrement. This is smaller. So when you found the smaller, you will stop. So I stop here. Again I check whether P is less than Q. Yes, P is less than Q. So swap. So in next iteration, it is like 77, 45, 37. It will become 10. It will become 90. Then 120. Then 1110. Okay. Now P is pointing here and Q is pointing here. I will check for the P and found that P is less than this one. I increment the pointer P and P is now pointing to the 90. Again I will compare 90 with 85. I found it greater and I will stop P here. I will not move further and then go to for Q. I will compare Q with 85 and found that it is greater, so I will update the pointer Q. So Q is now pointing to this element. I again compare Q with 85 and found that this one is smaller. I will stop Q here. Now when you stop Q, you can check that whenever the value of P is greater than Q, then one pass is completed and I have to swap the value of Q with the pivot element. So after this, the resulting array would be 10, 65, 50, 77, 45, 37, 85, 90, 120 and 110. So this is the new location for my pivot element and this is the K which is in this mentioned in this algorithm, the location of K. So this one is my one of the partition and this is another partition. All the elements in left hand side partitions are smaller than 85 and all the elements at the right hand side of the partition are greater than 85. So by this I divide my array into two sub-arrays of size n-1 elements, of having n-1 elements, and these sub-arrays are, one sub-array is smaller, containing a smaller element than the pivot, and other sub-array containing the larger element than the pivot. So I again apply the quicksort on this half and on this half. When you apply the quicksort on this half, the pivot element is considered as 10. And when I apply the quicksort on this half, the pivot element would be 90. Again, same, you can compare with two pointers. One is pointing to the second element and another is pointing to the last element. Similarly, here you can compare with the second element and the last element. After repetitive procedure until only one element is left, quicksort will be terminated and you will found a resulting array as sorted sequences. So if we analyze the time complexity required for this quicksort algorithm, we have to analyze the time complexity required for the partition. And we know that for n element, partition always return n minus 1 elements. And in this case, it will require order of n time. And both of these procedures will require, in worst case, they require n by 2 time. In worst case, the problem may be divided into half. One part is in k minus 1 and another part is k plus 1 to j, I to k minus 1 and k plus 1 to j. So in this case, so this would be the best case. In worst case, the recurrence would be different, in which the problem may be divided into n minus 1, 1 and n minus 1. So we will discuss it later. In best case, it may be considered that problem is divided just half. And in that one, the time complexity would be 2tn by 2 plus theta of n, and which is similar to the merge sort time complexity, that is order of n log n. Okay.